In this chapter, we're going to discuss the geometric tolerance called runout. Your objectives for this chapter are: describe the two types of runout tolerances, 2. Complete an interpretation drawing showing how each of the runout tolerances is measured, 3. Apply both types of runout tolerances on circular features and face surfaces. Number 4, specify runout tolerances using multiple datum feature references. That's old compound datum. And number 5, differentiate between the definitions of the following terms. So please refer to your objective sheet. Runout. A runout tolerance specifies the allowable surface variation relative to an axis of rotation. Tolerances define the amount of variable variation that's allowed, permissible variation. There are two types of runout tolerances, just two. One is called circular and one is called total. So circular runout and total runout. Let's talk about circular first. Circular runout. Surface variation is measured at each circular element of the part. So each measurement of multiple elements are evaluated separately. The largest reading is the circular runout for the part. So how we do this is we will spin the part about the datum axis and measure the full indicator movement at one position. That's when we talk circular. We leave the indicator at one position and do a full rotation. And then when it says each measurement of multiple elements evaluated separately, is I would move the indicator down the shaft, leave it in that position, and give it a full circle rotation again. Okay, so I have multiple measurements along the surface, but at each time the indicator is at the same spot. That's what they mean by circular runout. So for the feature control frame for a circular runout, it looks like this. We have our symbol, which is runout. The tolerance here is always a full indicator movement tolerance, and it's always at RFS, and it's always at regardless of material boundary, always. Now, multiple datum features are permitted. This is when we used a compound datum. Okay. And we can also use two primary and secondary datums. I'll show you about that. Circular runout applications. We can apply circular runout to cones. We can apply it to cylinders. We can apply it to spherical surfaces, flat surfaces, and then any surface with a circular cross-section centered on an axis. So here's how we apply circular runout to a cylinder. Okay, so here we have a cylinder. We have 3 steps on the cylinder. We have a runout tolerance of 5 thousandths to A being this diameter here, again, regardless of feature size, regardless of material boundary. This way we're showing you 3 ways to put a runout tolerance of 8 thousandths on this surface. We can apply it with a leader. We can apply to an extension line, or we can apply it to a dimension line. There's 3 ways to do this. Now, what does this mean? We have a tool, like a chuck for instance, that picks up the 562 diameter regardless of feature size. The chuck will clamp on that diameter regardless of feature size. So then we position our indicator on one of these circular elements, we spin the part all the way around, and we measure the full indicator movement. As long as it's less than 8 thousandths on the surface, it's good. It meets this 8 thousandths runout requirement. And then we would have to check it at several different places. So each cross-section runout measurement is independent. So we run it here, we go full circle, we move to the next one, we go full circle, we move to the next spot, go full circle. And that's how we check a runout tolerance. Now, runout tolerance may also be used on an internal hole. Okay, as long as we can spin it about this axis. Okay, so in this case, our datum axis is going to be established by this counterbore feature right here. And we're going to spin the part and check the run out of these circular elements inside this hole right here. Here's how we would check circular run out on a conical surface. We would chuck this up by datum M, and then we'd also, in this case, we have two datums. We have to chuck it up by this diameter, and we also have to simulate the face here for datum N. And then we spin the part around. We'll put our indicator at one of these circular elements, spin the part all the way around, move it to the next element, spin it all the way around, get the full indicator movement, and then move it to the next element, spin it all the way around. In this case, we have a spherical diameter, and again, it's the same thing. We're going to chuck it up by our diameter A. We're going to simulate datum B by touching this face. We're going to spin the part around with our indicator stationary, and it's going to give us a circular run out, full indicator movement for each one of these individual measurements. Here's how we would do it on a flat surface. Okay, in this particular case, what we have here is we have datum A, which is the cylindrical feature here, and we have a circular run out on the back face of this button. Okay, so what we would do is we would spin the part about datum A, we leave our indicator stationary to check this circular element, and then check this circular element, and then check this circular element. Individual measurements each have to be less than the 8,000th full indicator movements. I want to start this on the next movie. Thank you.